Hello everybody, welcome to today's lecture on material balance calculations for multi-unit processes with reactions. As I had promised in the previous lecture, today we will be looking at an example problem where the word problem needs to be converted into a flow chart before we perform the material balance calculations. It is important to convert word problems into flow charts and gain the experience and the skill set which is required for understanding the information that has been provided to us and then drawing flow charts based on that. So, this will help us in interacting with management. As engineers, we should be able to grasp what is being conveyed by the technical staff and the managers and try to convert it into technical information that can still be processed further. This is easy when we talk about single unit processes. So, we have done this before. When we did single unit processes, we identified the number of inputs and outputs, and we also drew the flow charts before we started performing the material balances. This is very straightforward in the single unit process. However, it is a lot more complicated with multi-unit processes because we need to understand how the streams are flowing from one of the units to the other. There could be streams which are leaving the system altogether, whereas there could be other streams which are being taken to the next unit for further processing. So, understanding this and converting the converting the word problem into a flow chart is a skill set which is gained over a period of time. So, here we will look at an example problem which is a reasonably complicated problem with multiple units, and we will try to draw the flow chart as best as we can and compare with what we have in the what we have been given in the textbook and try to perform material balances for that particular system. So, the example problem states that sorrel slag containing 70% titanium dioxide, 8% iron and 22% inert silicates is fed to a digester reacted with sulfuric acid, which enters as 67% aqueous solution. The reactions in the digester are given, where titanium dioxide reacts with sulfuric acid and iron also reacts with sulfuric acid. Both reactions go to completion. The theoretically required amount of sulfuric acid for the sorrel slag is fed. Pure oxygen is fed in the theoretical amount for all the iron in the sorrel slag. Scrap iron, which is pure iron, is added to the digester to reduce the formation of ferric sulfate to negligible amounts. 36 kilograms of scrap iron is added per kilogram of sorrel slag which is fed. The products of the digester are sent to the clarifier, where all the inert silicates and unreacted iron are removed. The solution of TiOSO4 and FeSO4 from the clarifier is cooled, crystallizing FeSO4, which is then completely removed by a filter. The product TiOSO4 solution from the filter is evaporated down to a slurry that contains 82% TiOSO4. The slurry is then sent to a hot air dryer, from which a product of pure hydrate, which is TiOSO4H2O, is obtained. The hydrate crystals are sent to a direct fired rotary kiln, where the pure TiO2 is produced according to the following reaction, where the hydrate is converted to TiO2 and H2SO4. This reaction also goes to completion. Using the basis of 100 kilograms of sorrel slag feed, you have been asked to calculate the kilogram of water removed by the evaporator, the exit kilogram of water per kilogram of dry air from the dryer if the air entered contains 0.036 moles of water per mole of dry air and the air rate is 18 kilomoles of dry air per 100 kilograms of sorrel slag. And you have also been asked to calculate the kilograms of product TiO2 produced. So, before we start with any of the material balances, we now need to draw a flow chart. As you saw, there are multiple units in this process, and we need to read this problem one more time carefully for each unit, identify what are the inputs and outputs, which of the outputs are actually taken for further processing and which of the outputs actually leave the system. So, let us do that by drawing the flow chart. In the first sentence of the problem, it is stated that sorrel slag containing 70% TiO2, 8% iron and 22% silicates is fed to a digester. So, which means the first process or the first unit we have in the process is a digester. So, let us first draw a digester. So, this is the digester. So, this digester is fed with sorrel slag. So, this is the first information we have. This sorrel slag then reacts with sulfuric acid, which enters as 67% aqueous solution. This means that we have another input which is 67% aqueous solution of H2SO4. So, that would be an additional input for the system, which is 67% H2SO4, which is aqueous solution. And then what else do we have? We have the reactions given, and then it is also told that the theoretically required amount of sulfuric acid for sorrel slag is fed, and pure oxygen is fed in the theoretical amount for all the iron in the sorrel slag. So, in addition to these two inputs, you also have another input which is the pure oxygen, which is fed to the digester. So, you have pure oxygen fed to the digester. Then it is also said that scrap iron, which is pure iron, is added to the digester to reduce the formation of ferric sulphate to negligible amounts. So, you also have scrap iron added to the digester. So, it has been told that 36 kilograms of scrap iron is added per kilogram of sorrel slag. The products of the digester are then sent to a clarifier. Everything that comes out of the digester then enters into a clarifier. Everything that comes out of the digester then enters the clarifier. So, this means whatever we have out of the digester enters into the clarifier. So, here all the inert silicates and unreacted iron are removed. So, this means these components are leaving the system. Inert silicates and unreacted iron are actually removed from the system. So, which would leave the overall system. So, the next step is the solution of TiOSO4 and FeSO4 from the clarifier is cooled, which causes the crystallization of FeSO4. So, this means whatever is remaining here, the solution of TiOSO4 and FeSO4 is cooled. So, you have a heat exchanger and a crystallizer which cools it, and crystals are formed. So, this slurry is then fed to a filter. So, where all the crystallized FeSO4 is removed and only the solution of TiOSO4 leaves. So, you have a filter. So, this would be a filter, and from the filter all the FeSO4 is leaving the system, and you have the solution of TiOSO4 then taken to the evaporator. So, it goes to an evaporator. So, what is given here is this solution is then evaporated down to a slurry that contains 82% TiOSO4. So, which means water is removed from the system. So, you have water leaving as water vapor from the system, and you have a slurry which is then sent to a dryer, from which you have the pure hydrate formed. So, this has been also given as a hot air dryer. So, this enters into a hot air dryer. So, a hot air dryer is the one where you have hot air entering the dryer in addition to the wet component, and this hot air would help you in drying the component. So, in addition to this, you also have air entering, and you would have air carrying water leaving the system. So, this would be air which is entering, and you would have air which is wetter leaving the system. So, the slurry which is now slightly dried is then taken to a rotary kiln, where it is dried completely to remove the H2SO4 based on the reaction. So, the hydrate crystals are converted to TiO2 and H2SO4. So, this goes to a rotary kiln, and from the rotary kiln you take out TiO2, which is the product, and H2SO4 also leaves the system. So, this gives you the flow chart for performing calculations related to any material balance for this system. So, let us now compare it with what is given in the textbook. So, if you look at the system, it is very similar to what I have drawn, and this clearly explains the process. Now, let us go about solving this problem, trying to identify which system to start with, what basis to use, and so on. So, the basis for the problem has already been given in the problem statement. We have been told 100 kilograms of sorrel slag is entering into the system, and we have been asked to calculate different things using this basis. So, we will start the problem with the basis of 100 kilograms of sorrel slag. So, basis is 100 kilograms of sorrel slag. Now, if you look at the aspects which we need to calculate, we need to look at the kilograms of water which is removed from the evaporator, which is this stream, and we also need to calculate the exit kilograms of water per kilogram of dry air from the hot air dryer. So, which is basically this stream, and we need to calculate the kilograms of product TiO2 produced, which is this stream. So, these are the three components which we need information on. So, our problem statement asks us to find information about these three streams. So, this means we do not care about what information is present in this stream or this and so on. So, as we do not need to know about these streams, what we can do is we can choose a system which engulfs these particular streams. So, taking that into account, we want the streams for water, air plus water and TiO2 to be leaving the system. So, to solve the first part of the problem, we need to make sure that this particular stream is crossing the system boundary. The other streams in between do not have to cross the system boundary. So, based on that, we will first choose the system as this particular system. So, when you do this, what happens is you have sorrel slag, scrap iron, H2SO4, pure oxygen all being fed to the system, and you have FeSO4, inert silicates, unreacted iron and water leaving the system along with the slurry for TiO4. So, using this particular system, we can perform material balance calculations to get the information regarding this particular stream, which is water which is evaporated in the evaporator. As we need to use the stoichiometry given in the reactions, we will convert the mass into moles, so that we can directly use the stoichiometric coefficients and perform calculations to get the generation and consumption terms. Taking that into account, we first need to know the molecular weight of titanium and iron. So, molecular weight of titanium is 47.9 kilograms per kilomole, and molecular weight of iron is 55.8 kilograms per kilomole. So, now that we have this, we have to calculate the number of moles of TiO2 and iron and H2SO4 that are being fed. So, we know that 100 kilograms of sorrel slag is entering. So, this contains 70 kilograms of TiO2 and 8 kilograms of iron, and the rest is inert silicates. So, now this 70 kilograms of TiO2 would then be 70 divided by 47.9 plus 32, giving you a value of 0.876 kilomoles. The number of moles of 8 kilograms of iron would be 8 divided by 55.8, giving you a value of 0.143 kilomoles of iron. The problem statement tells us that H2SO4 is fed based on the theoretical requirement of sulfuric acid as per the sorrel slag. This means the amount of sulfuric acid which is required to react with TiO2 and iron has been fed. So, based on that, the stoichiometry, looking at the stoichiometry, we know that 1 mole of TiO2 reacts with 1 mole of H2SO4. Similarly, you have 1 mole of iron also reacting with 1 mole of H2SO4. So, this means H2SO4 fed would be equal to 0.876 kilomoles plus 0.143 kilomoles, which is the number of moles of TiO2 and iron fed in the form of sorrel slag. So, using this we get the amount of TiO2 amount of H2SO4 fed is 1.02 kilomoles, and this would weigh 100 kilograms. We also know that pure oxygen is fed. So, we need to calculate how much of pure oxygen is fed. Pure oxygen is fed at the theoretical requirement of iron, which is fed through the sorrel slag. So, we know that 0.143 kilomoles of iron is fed, and 1 mole of iron reacts with half a mole of oxygen based on the stoichiometry of the reaction given. So, this means 0.143 kilomoles of iron would require 0.143 kilomoles of iron will require 0.143 divided by 2 kilomoles of oxygen. So, pure oxygen fed would be equal to 0.143 times 0.5 times 32, which is 2.29 kilograms. So, we also have an information that 36 kilograms of pure iron was fed per kilogram of. Now that we have the information about the sorrel slag, H2SO4 and O2, the other component which is fed is the scrap iron. We have been told that scrap iron or pure iron is fed at a rate of 36 kilograms per kilogram of sorrel slag. So, this means pure iron fed would be equal to 36 times 100, giving you 3600 kilograms of pure iron being fed. In the problem, there have been 2 reactions which are taking place in the digester, which are TiO2 plus H2SO4 gives TiOSO4 plus H2O, and the other reaction is Fe plus half O2 plus H2SO4 gives FeSO4 plus H2O. So, taking the first reaction, the amount of TiOSO4 that would be produced is 1 mole of TiO2 will produce 1 mole of TiOSO4 if the reaction goes to completion. The problem statement tells us that both these reactions go to completion in the digester. This means the number of moles of TiOSO4 formed would be equal to the number of moles of TiO2 which is fed. So, we know that 0.876 kilomoles of TiO2 is fed. This implies 0.876 kilomoles of TiOSO4 is generated. Looking at the system that we have chosen, which is basically this, TiOSO4 leaves only through the stream. TiOSO4 does not leave through the other streams. This stream has only unreacted iron and inert silicates, and this particular stream has only water, this particular stream has only FeSO4. So, this means TiOSO4 leaves only through this particular stream, and based on the information from the problem, we know that this is 82% TiOSO4 solution. So, the rest has to be water. So, we need to calculate the amount of water which is leaving through this system. So, we now have information about water which is present in this particular system, particular stream, and we know that there is some water entering here through the H2SO4 stream, and water is not leaving through the inert silicates or through the FeSO4, water is leaving only through this, but these two particular streams. So, based on these information we can now start writing a balance equation for water, so which is exactly what we are going to do now. Based on this information we can start writing a water balance equation. So, the water balance equation for the system which is chosen would start from input minus output plus generation minus consumption equals accumulation. At steady state there will not be any accumulation. Water is not being consumed by any of the reactions which are happening in the digester, that means consumption terms will go to 0. So, you are left with input, output and generation. So, we need to calculate the output through the water vapor stream. So, this output has two streams, one is your TiO-SO4 slurry stream and the other is your H2O stream which is the water vapor. So, input water needs to be calculated first. Input is from the H2SO4 stream. We know that 100 kilograms of sulfuric acid is fed and this forms a 67% solution. So, this implies 100 kilograms of H2SO4 forms a 67% solution. So, water in this stream would be 100 divided by 0.67 times 0.33. So, this gives you a value of 49.25 kilograms. So, 49.25 kilograms of water is fed through the H2SO4 stream. Now, we need to calculate the amount of water which is leaving through the TiO-SO4 slurry stream. So, let us call that output 1. Water output 1 would be equal to the amount of water leaving through the TiO-SO4 slurry. So, based on the calculations we have performed, we know that 0.876 kilomoles of TiO-SO4 was produced. So, this 0.876 kilomoles of TiO-SO4 would weigh 140.07 kilograms. So, this 140.07 kilograms constitutes the 82% solution or the slurry which is leaving the evaporator. So, this implies water here in TiO-SO4 slurry. So, water in the TiO-SO4 slurry will be equal to 140.07 divided by 0.82 times 0.18, giving you a value of 30.75 kilograms. Now, we need to calculate the amount of water which is generated. So, water generated is equal to what? So, based on the stoichiometry, for every mole of H2SO4 consumed, there is 1 mole of H2O produced. There are two equations, both of which follows the same stoichiometric ratios. So, this means for every mole of H2SO4 consumed in the digester, 1 mole of H2O would have been produced. Based on the information that has been given to us, we know that 1.02 kilomoles of H2SO4 has been consumed. So, 1.02 kilomoles of H2SO4 consumed would have resulted in the formation of 1.02 kilomoles of water. So, this implies water generated would be equal to 1.02 times 18, giving you a value of 18.36 kilograms. So, now that we have all these terms, we can calculate the amount of water leaving in the form of water vapor from the evaporator. So, let us call that W out would be input minus output 1 plus generation. So, this is input value is 49.25, output is 30.75 and your generation is 18.36, giving you a total amount of water leaving the system as 36.86 kilograms of water vapor leaving the evaporator. So, with this we have calculated the first part of the problem. In the second part of the problem, we have been asked to calculate the exit kilograms of water per kilogram of dry air from the hot air dryer if the air entering contains 0.036 moles of water per mole of dry air, and it has also been given that the air rate is 18 kilomoles of dry air per 100 kilograms of swirl slag which is fed. So, we need to basically calculate the amount of water which is leaving through the stream. So, based on the information we have, we know that the air entering here, the air input has 0.036 moles of H2O per mole of dry air, and air is fed at a rate of 18 kilomoles of dry air per 100 kilograms of swirl slag. So, based on the information given to us in the problem and the calculations we have performed, we know that water is entering into this dryer through the slurry here and water is leaving as evaporated water vapor along with the air. In addition to that, water is also accompanying TiOSO4 in the form of water of hydration with the TiOSO4 hydrate crystals which then enters into the rotary kiln. As we need to calculate the information about the stream here, the system we choose would be only the dryer. Taking the dryer as the system, let us now calculate the water which is leaving along with the air. Now, water balance across the dryer would basically start from input minus output plus generation minus consumption equals accumulation. At steady state there is no accumulation. You have input for water both through the air and through the slurry, and you have output for water through the air and in the form of water of hydration. You do not have any generation, you do not have any consumption. So, it would be input equals output. So, now we need to calculate the amount of water which is leaving in the form of water of hydration and the amount of water which is entering through these two streams. So, let us first calculate the input water streams. So, input for water in the form of slurry, how much water is being fed? We know that 82% TiOSO4 is present in the slurry, and we have already calculated that the remaining amount would be water and the value is 30.75 kilograms. So, water entering through the slurry is 30.75 kilograms. The water in the inlet air has been given in terms of moles per mole of dry air. So, we know that there is 0.036 moles of water per mole of dry air, and we have also been told that 18 kilomoles of dry air is fed for 100 kilograms of swirl slag. As we have 100 kilograms of swirl slag as the basis, we know that 18 kilomoles of dry air has been fed. Water in the inlet air would be equal to 18 times 0.036 kilomoles. So, this equals 0.648 kilomoles. So, this 30.75 kilograms can also be converted to moles and by dividing it with the molecular weight, and we end up with 1.708 kilomoles. So, we have now calculated the amount of water which is entering into the system. We now need to calculate the amount of water which is leaving the system in the form of water of hydration. Based on the stoichiometry for the water of hydration, we know that TiOSO4 dot H2O is the hydrated crystals. This implies 1 mole of TiOSO4 uses up 1 mole of water as the water of hydration. We know that 0.876 kilomoles of TiOSO4 has been formed and it is entering into the dryer. So, this would use 0.876 kilomoles of water in the form of water of hydration. So, water leaving as water of hydration would be equal to 0.876 kilomoles. So, using all this information and substituting them back into the equation, we can get the amount of water. Using all this information and substituting them back into the water balance equation, we can calculate the amount of water leaving with the air. So, that would be water in inlet air plus water in slurry would be equal to water in exit air plus water of hydration. So, this means it is 0.648 plus 1.708 equals water in exit air plus 0.876. So, you have water in exit air as 1.48 kilomoles, which is equivalent to 26.64 kilograms. Now that we know 26.64 kilograms of water is leaving with the air, we still need to calculate the kilograms of water per kilogram of dry air which is leaving the system. So, we know 18 kilomoles of dry air is fed. So, that means the mass of dry air fed would be 18 kilomoles times molecular weight of dry air, which is 28.84 if we assume 79% nitrogen and 21% oxygen. The molecular weight for dry air would be 28.84, and using this, mass of dry air would be equal to 519.12 kilograms. So, for 519.12 kilograms, you have 26.64 kilograms of water leaving. So, water, kilograms of water leaving per kilogram of dry air would be equal to 26.64 divided by 519.12. So, this would be equal to 0.0513 kilograms per kilogram. So, with this we have the information for the second part of the problem. So, the third part of the problem asks us to calculate the kilograms of TiO2 which is leaving the system. So, this is very simple and straightforward. All we need to do here is choose the overall system. We know that titanium is not leaving the system, titanium element is not leaving the system through any stream other than this particular stream. This means all the TiO2 which is entering into the system in the form of the Sorel slags would only be leaving the system through the TiO2 stream leaving the rotary kiln. Knowing that input equals output would be the simplest equation we use. So, taking that into account for Ti, which is elemental balance for titanium oxide. So, elemental balance for titanium, we know that whatever titanium is entering would be leaving in the form of TiO2 again. So, taking this into account, the amount of TiO2 leaving the system, mass of TiO2 product would be equal to mass of TiO2 fed, which is 70 kilograms. So, with this we have solved this problem. So, we started with the word problem and drew the flow chart based on the information given, and we have performed all the material balances required to calculate all the information that has been asked for. With this, we will come to the conclusion for standard reactions in multi-unit processes. In the next lectures, we will look at certain specialized reactions such as biochemical reactions, which would be suitable for people with biotechnology background, and also look at combustion reactions, which are very critical in chemical industries, and students with a chemical engineering background might be interested in learning that. We will look at these two types of reactions and see how to perform material balances for such reactions. Thank you.